Hi, I'm Joshua Turcotti, and this is going to be a webcast version of CS70 discussion number 7. For each question, I'm going to explain the question and then walk through the solution to the question. If at any point you feel like you understand it well enough in order to write out the rest of the solution yourself, you should pause the video and go ahead and do so. We're going to start with number 1. We're given a problem where we have n different spots, x1 through xn. And these are all potential spaces that we could plant a tree. Each of these values represents the number of apples that we'd obtain if we were to plant a tree at that position. And our goal is to maximize the number of apples, with the constraint that 2 trees cannot be planted right next to each other. For example, we could plant trees at positions 1, skip 2, and plant at position 3, but we could not plant in both positions 1 and 2. Just trying to enumerate all the possible ways that we could plant trees would be time exponential in n, which is clearly infeasible. So we need a more intelligent way to go about this. The problem will walk us through coming up with this intelligent way, which has the name DP, dynamic programming, through several steps. First, we're going to dismiss the obvious algorithms that we could go for. The first one that we might think is optimal is just considering 2 possible ways of planting trees, on all the odd-numbered spaces and on all the even-numbered spaces. Both of these will not give us the optimal result in all cases, and we can see this with some quick counterexamples. The way to think of a counterexample for this is to see one where the optimal arrangement contains both an odd-numbered tree and an even-numbered tree. Can we think of such an arrangement? Well, yeah. We can give a very high number of apple payoff to an odd-numbered tree, let's say in position number 1, followed by another very high payoff to an even-numbered tree, let's say in position 4. Note that because there are 2 empty spaces between positions 1 and 4, it's possible to plant both of these trees, skipping the very low payoff trees in between them, which will say both produce 1 apple each. Here, planting trees in all the odd-numbered spaces and all of the even-numbered spaces would each only give us 11 apples, as opposed to the maximum of 20 apples that we could get. So this approach is clearly suboptimal. We can also look at the next possible approach, a sort of greedy approach, where we always look at the highest possible tree value that we could plant, the highest number of apples that we could get, and then just kind of keep going, eliminating impossibilities as we plant trees. This seems smarter than just the odd and even approach, but there are also obvious counterexamples where this doesn't work. You can think back to the greedy edge cover problem from the previous discussion. We have a similar counterexample here, where we can force the greedy algorithm to pick a very high number of apple position, let's say number 2 out of 3, but that in doing so, it actually eliminates 2 other spots that could have had a higher possible weight if they were chosen instead. In this example, the greedy algorithm will choose a 10 apple output, whereas there is a possible 12 apple output. Clearly, this algorithm as well is suboptimal. So now we will go about determining the optimal algorithm. We'll begin with the idea, which is a very key one, of subproblems, which are at the heart of DP. Here, our subproblems are just going to be the maximum number of apples using only spots 1 through I. This is the key point. We're restricting the scope of our problem. So, let's look at some simple examples of this. f of 1. What's the maximum number of apples that we can get using only the first spot? Well, this is to plant at the first spot. This is the number of apples that we get from planting at the first spot. What about 2? What if we have the option to plant at either of the first 2 spots? Then what's our maximum possible number of apples? Well, we can only plant at one of these 2 spots, so we simply choose the maximum of x1 and x2. These are the values for f1 and f2, our first 2 subproblems. Now, we're going to figure out how to compute larger fi in terms of smaller ones. Namely, we have to break this down into some cases. The first case that we're going to look at is when the optimal way to plant trees on spots 1 through I does not place a tree in spot I. Clearly here, since we're allowed to place trees now in any spot 1 through I minus 1, the optimal number of ways to plant trees in spots 1 through I is equal to the optimal number of ways to plant trees in spots 1 through I minus 1. So we can see that one possible value, the value in which we choose not to plant a tree at spot I for fi, is equal to fi minus 1. Now, we also have another option. We can choose to plant a tree at spot I. If we choose to do this, then we note that it is, so let's say we choose to plant a tree at spot I. We note that now it's infeasible to plant a tree at spot I minus 1. So when we're trying to express fi here in terms of smaller subproblems, the weight, the value, the number of apples that we're going to get is going to include x sub I, but it's not going to include I minus 1. It's only going to include any possible trees in I through I minus 2. So here, we're going to have f of I equals xi plus f of I minus 2. So our 2 options for fi are fi equals f of I minus 1, or f of I equals xi plus f of I minus 2. This expresses the choice to plant a tree or not to plant a tree at spot I. We can combine these 2 results in order to get a complete approach for computing fi. We combine them by maximizing. F of I is just going to be equal to the maximum of the choice not to plant a tree at spot I, which gave us a payoff of fi minus 1, and the choice to plant a tree, which gave us a payoff of xi plus f of I minus 2. And this function is constant time to compute. Given that we already know f of j, right, for all j less than I, this is exactly 3 operations, an addition and then a comparison and an assignment in order to get the value of f of I. This achieves the desired constant time for each step. We can now analyze the total runtime of this algorithm, and we can see that we have to perform exactly n of these substeps, n of these individual 2-way maximizations, in order to go from our initial value of f1, which we remembered was just equal to f1, to our value for f2, which now we can even plug into this above formula, and c is equal to the max of f of I minus 1, which is f1, and just x2, because I minus 2 is 0, which is in accordance with the value that we computed right here. f1, f2, all the way to fn. And fn is going to be the maximal possible payoff for when we can plant trees at any of the first n spots. And since each step here is time O of 1, and we have n steps. The total runtime for this DP approach is linear, O of n. This is how we've figured out a linear time DP algorithm for what otherwise would have been an exponential time search through possibilities. Now, we're going to apply this DP thought process again to another problem, string shuffling. Here, we have two input strings, X and Y, both consisting of just some stream of characters. And we're going to define an interleaving of X and Y, where an interleaving is a sequence of all the characters from X and Y possibly occurring in such a way that all of X does not come before all of Y, or all of Y does not come before all of X, but that some of X, let's say the first two characters of X appear, then the first character of Y, followed by the third character of X, followed by the second character of Y, such that they interleave with each other. In the case when when X and Y have distinct characters, it can be very easy to look at this interleaving and determine how it was obtained from X and Y, or even whether or not it was possible to obtain it from X and Y. In general, if there are a lot of repeated characters between X and Y, it could be very difficult to look at a string such as this one and actually determine if it's possible to form as an interleaving of X and Y. We're going to give a dynamic programming approach to figuring out this problem of whether or not a given string can be formed as an interleaving of X and Y. If you have an idea for the subproblems here, you should pause it and write down what these subproblems could be. Now, we're going to state what we want our subproblems to be. Namely, we're going to define our subproblems. We'll give them the value v of ij, where I is less than or equal to n, which is defined as the length of our input string x, and j is less than or equal to m, which we'll define as the length of our input string y. So you can see right away that we have nm subproblems. We're going to define this to be the question, is it possible to form the first I plus j characters of z, this is the substring in positions 1 through I plus j of z, from x, the first I characters of x, and the first j characters of y. So we can immediately see, first of all, that v sub nm is just the question, is it possible to form z from x and y? And we can see that the small values, v of 1, 0, for example, are really easy to compute. I'll show you how in a second. But given that all of these small values, like v of 0, 1 and v of 1, 0, are easy to compute, and given that v of nm is the desired answer to our entire problem, we can see that all we have to do in order to come up with an efficient algorithm for this problem is find a way to go from smaller subproblems, v1, 0 and v0, 1, to larger subproblems like vnm for general m. Let's see how we can possibly go about this. So, we want to look at v, not even vnm, but just vij, for arbitrary I and j. How do we know if it's possible to form the first I plus j characters of z from the first I characters of x and the first j characters of y? Well, we can look at the I plus jth character exactly of z, zi plus j. If z is really an interleaving of x and y, then this must be equal to either the ith character of x or the jth character of y. Do you see why this is? Think about it for a second. Let's say we have x, has a bunch of characters, and then ends in an a. At least this is the first I characters of x. Similarly, y, the first j characters of y, has a bunch of random stuff, and then ends in a b. If z is really an interleaving of x and y, we know that the I plus jth character of z has to be either an A or a B. There's really no other option. So, we look at each of these two cases individually. What happens if the I plus jth character of z comes from the ith character of x? Well, then it must also be true that, well, first of all, it must be true, as we examined over here, that z I plus j equals x sub I. And we're going to use the wedge symbol for and it must be true that it's possible to form the previous segment of z, which in this diagram is everything leading up to the A or B, it's possible to form this from x, the first I minus 1 characters of x, and the first j characters of y. Because, this is simple enough. If we can just take the first I minus 1 characters of x and the first j characters of y, and we can form from them the first I plus j minus 1 characters of z, then all we have to do is look at the next position in x, which is the ith position. We can append that character to z, and then we will have formed the first I plus j characters of z. So this is one possibility. Note that this entire expression, in the language of our subproblems, is just v I minus 1 comma j. Now, there's another possible way that z I plus j could be expressed as an interleaving of xi and yj, and that's that the I plus jth character of z is equal to the jth character of y. That's up here when we got the I plus jth character of z, not from the last character of x, but from the last character of y. So we got this b instead of this a. In order for this to give us a valid way, in order for this to give us a valid interleaving for the first I plus j characters of z, we also have to have that we can form z I plus j minus 1 from the first I characters of x and the first j minus 1 characters of y. In the language of our subproblems, this is equal to v I j minus 1. So we can now very concisely express a logical way to give vij in terms of vi minus 1j and vi j minus 1. We'll write it all out right here. V ij is equal to the expression z I plus j equals xi and v I minus 1j, or this is going to be our disjunction symbol, z I plus j equals yj and v of I j minus 1. This is our complete expression of our subproblem solution. This is analogous in part 1 to this expression for fi. And just like part 1, this is constant time to compute. It's just 3 logical operations plus 2 comparisons. We can also now think of the order in which we need to compute these subproblems, and we can basically see that it suffices to consider these subproblems in the order of the sum of I plus j. Because if we're trying to compute Vij, right? The only dependencies for computing this are Vi minus 1j and Vij minus 1. And we can see that the sum of the arguments here goes from I plus j to I plus j minus 1. In other words, to compute all v sub ij such that vi plus j equals n, all we need to know ahead of time are all vij such that I plus j equals n minus 1. This gives us the order in which to compute these subproblems. Namely, we can even think of this as kind of like a matrix. Yeah, so we'll put this under part 2 for now, and we'll see why in a second. But we can think of this as a matrix, where this dimension right here represents x. So this is n. And this dimension right here, that's an ugly line, represents y, so length m. And the entry of this matrix, we'll call this matrix A, the entry ij is just equal to v ij. And our n here is just going to be which diagonal, and these are sort of like anti-diagonals, which diagonal here we're on. And we saw from we call this the recurrence relation. We saw from our recurrence relation that to compute any value along diagonal n, all we need to know are the values on diagonal n minus 1. We start off with the simple ones, v10 and v01. Those are going to be the first 2 entries. And then from there, we just iterate along each diagonal, computing each of the values. This is just simply going to be time O of nm. Which is satisfactory. We can also think, though, of the amount of space that's going to be required. Before we think of the amount of space that's required, I want to make sure that you're actually convinced of the correctness of this algorithm. So take a moment, look again at our derivation for the recurrence relation, which we have right here. This is our recurrence relation. Take a look again at this recurrence relation and the way we got that. Be convinced of the logical correctness of this, and then see that we can efficiently compute it in this planning scheme along diagonals, going from smaller diagonals to larger diagonals, starting with these trivial cases right here, which correspond to the smallest diagonal, and ending with our big solution to the entire problem, which is the value right at the bottom right corner of the matrix. We can see that there are O, N, M of these subproblems, and each one is constant time to compute, which gives us our overall runtime of O, N, M. That's not how you write that. Our overall runtime of O, N, M. Now, what part 2 right here asks us to take a look at is not only the runtime complexity of this algorithm, but also the space complexity. If we really just naively implement this matrix scheme that I described right here, then we're going to end up also using O of NM space. We can make the clever observation that every time we compute a diagonal, we can actually forget about the previous diagonal. Because when we're computing diagonal n, we only need to know the values of diagonal n minus 1. We don't care anymore about the values on diagonal n minus 2. So all we have to store at a time is the value of two different diagonals. The one we're currently computing, that's not what I meant to do. The one we're currently computing, and the one right before it. And instead of O and M space, that's just O of n. It's going to be the O of the maximum of the two. Or rather, the minimum. O of min and m. Right? We can see this because no diagonal can possibly include more than the minimum of n and m values in it. So all we have to remember is two of these diagonals. And that'll be our space complexity for this DP algorithm. So, what looked at first like a relatively challenging, slightly intractable problem, determining whether or not this jumbled up string z, could actually be formed as an interleaving of x and y, turns out to have a very nice DP algorithm for solving it. Now, we have two more problems left on this discussion worksheet, numbers 3 and 4. Number 4 is another very approachable DP problem of the style you could see on a midterm or a final, like 1 or 2. Number 3 is a substantially more difficult problem. So I think we're going to actually save number 3 for the end, and we're going to move on to number 4 right now. For number 4, we're going to consider another game. In this game, we have n cards in a line. Or we'll even, instead of just writing numbers, we'll give them values. We'll say they have values A1, A2, A3, all the way up to AN. And this is a game where two players alternate. One player gets to choose a card from either end. Let's say they choose the left end, and then they can add a 1 to their score. This is player 1. This is player 2. The next player now can look at A2 or AN, because those are the new ends, and decide which of those they want. Let's say they choose AN. They can keep going. Now player 1 maybe could choose either A2 or AN minus 1. Let's say they choose AN minus 1. They add that to their score. Then maybe player 2 adds AN minus 2 to their score. Player 1 adds A2 to their score, and so on. Eventually, they run through the entire line of cards, and whoever has the higher score wins. So, we have two players. We're going to call them Ning and Evan. Ning proposes a greedy strategy, which might be the first thing a lot of us would think of. Whichever card is bigger on the first move, A1 or AN, just take that card. Just like in question number 1, we're going to show why this greedy strategy doesn't actually work by coming up with a counterexample. Coming up with counterexamples is a really, really important skill for algorithm analysis and design. So see if you can pause for a moment and actually come up with a counterexample. We're going to construct a counterexample like we always do. We're going to force Ning, with the greedy strategy, to make a bad decision. We're going to force her to make a bad decision by taking advantage of her greediness. We're going to give her a 2 or a 3 to pick from for her first move. Since she's greedy, she'll obviously pick the 3. We'll make this a bad decision by causing the choice of the 3 to expose a really, really high value card to the second player, Evan. We can see that by choosing 3, we allow Evan to choose the 100. Whereas, if we insert another low value card between the 2 and 100, let's say just another card of value 1, we could have forced Evan to choose either a 1 or a 3. If we had picked the 2, Evan would have picked the 3. We would have gotten 2, Evan would have gotten 3, and we would have gotten to take the 100, leaving Evan to take the 1, giving us, Ning, a score of 102, and Evan a score of 4, if we had picked the 2. So we would have won by 98 points if we'd picked the 2 first. Instead, with our greedy strategy, we picked the 3 first, which then allows Evan to pick the 100. And as you can see, we're already hopelessly behind and we're going to lose by 90 plus points. This is a counterexample showing why the greedy strategy doesn't work. Now, just like number 1 again, we're going to come up with a DP approach that does work. We're going to come up with this by looking at subproblems. We're actually going to go through a couple stages of decomposition of these subproblems. Here's the first stage. The first stage, we're going to use V again, or maybe we'll use a different letter. Choice of letters is one of the greatest acts of creativity we have in algorithm analysis and design. Let's go for S. Sij is going to be defined as the best score we can obtain when we see cards I through J on our turn. So we can see immediately, just like in problem 2, that we have two extremes of cases. We have the really small cases, let's even call these inclusive bounds. We have the really small cases, like S5, which is we only see the card 5 on our turn, in which case our value is just going to be A sub 5, the value of the 5th card. These are really easy to compute. All of these. We have these really small cases all the way up to the really big case, S of 1n, being equal to the optimal score that we can obtain in the entire game. Since we've seen that we have really small cases that are really easy to compute, and a really big case that's a solution to the desired problem, all we have to come up with is a recurrence relation for larger values of S in terms of smaller values of S. Well, just like in both of the previous parts, we have to think about a decision that we can make. In question number 1, the decision was whether or not we include the ith tree in our optimal output. In question number 2, the decision was whether or not the I plus jth character of Z came from X or came from Y. Here, the decision is going to be whether or not we pick the left card or the right card. For ease of notation, we're actually going to further decompose our subproblems a little bit into 2 more. L sub ij and R sub ij. Maybe you can guess that the L and the R stand for left and right. L sub ij is going to be the best score we can obtain when we see it cards I sub j on our turn and pick the left one. R sub ij is going to be equal to the best score we can obtain when we see cards I sub j on our turn and pick the rightmost one. Now, all we have to do is come up with some math to relate these subproblems to each other. The first thing that we'll write down, we'll go sort of top down, is to say that V sub ij is just equal to, I hope you can guess this expression, the max of L sub ij and R sub ij. The best score we can obtain when we see cards I through j is the maximum of the best we can obtain choosing the left and the best we can obtain choosing the right. Now, let's see if we can express L sub ij and R sub ij in terms of smaller subproblems. Let's start with L sub ij. Well, we have to make an assumption here, since this is a 2-player game, about how our adversary is going to play. Let's scroll up and see what that assumption is. Assuming he is playing against Ning, and Ning is using a greedy strategy. So, we're going to figure out the best possible score we can obtain here, assuming that our opponent uses a greedy strategy. Well, what does that mean? Since we chose L, first of all, we know that we're going to pick the leftmost value. which is just a sub I. Now, what's the next set of cards that we're going to see? Well, the next set of cards that we're going to see is going to be either a sub I minus 2 through a sub j, or a sub I minus 1 through a sub j minus 1. And this depends on which card our opponent, Ning, chooses. If after we choose to take a sub I, Ning chooses to take a sub I minus 1, then we're only going to have a sub I minus 2 through a sub j to look at. But if Ning takes card a sub j, then instead we're going to have a sub I minus 1 through a sub j minus 1 to look at. And what does this depend on? This is, since our opponent, Ning, is playing with a greedy strategy, Ning will choose a sub I minus 1 if a sub I minus 1 is greater than a sub j. And otherwise, they'll pick a sub j. And this is when a sub j is greater than a sub I minus 1. We have to do a little bit of tie resolution here. We have to just assume a behavior for what Ning will do if the two cards are equal to each other. And we'll say Ning's a lefty and chooses the leftmost card. So if a sub I minus 1 is greater than or equal to a sub j. Now, we'll write this down a little bit more explicitly. Our condition for Lij, we'll say it's equal to a sub I plus, we're really just rephrasing right here, L I minus 2 through j, right? Sorry, not L, V. Because, just because we chose to go left when we were looking at Ij, doesn't mean that we have to choose to go left again when we're looking at I minus 2 through j. When it comes time for us to look at I minus 2 through j, we're simply looking at our best possible overall score, choosing left or right. And once again, this condition is our opponent's choice. So this right here is our recurrence relation for L sub ij. Similarly, we can write out the recurrence relation for R sub ij. This will be another good moment to pause and see if you can write down yourself the recurrence relation for Rij. Rij is equal to A sub j, because we choose the rightmost card, plus first choice. We can think, what if Ning takes the leftmost card? Then our choices for the next turn will be S sub I minus 1 through j minus 1. That's if Ning chooses the leftmost card, which occurs if A sub I minus 1 is greater than or equal to A sub j minus 1. If A sub I, we chose to choose card number j, so Ning sees cards I through j minus 1. If A sub I is greater than or equal to A sub j minus 1, Ning will choose A sub I, leaving us with cards a minus 1 through j minus 1 to look at. Otherwise, we'll be looking at cards I through j minus 2. Now, we've written down what look like satisfactory recurrence relations for both L and R. Will these actually work? When you're writing DP problems, after you think you've come up with your recurrence relations, it's really important to step back and say, do we have any circular dependencies? Are we relying on a solution that relies on ourself in order to compute? We have to prove that there's actually a valid order to compute all of these S sub ij's in, such that when it comes time to compute S sub ij, we already have all the other information that we need in order to compute it. So let's make sure of that. What do we need in order to compute S sub ij? Well, we need, I used a V right here. Well, we need Lij and Rij. What do we need in order to compute Lij? We need S sub I minus 2j and S sub I minus 1 j minus 1. What do we need to compute r sub ij? We need s sub I minus 1 j minus 1 and s sub I j minus 2. So to compute this one larger piece of information, we need these 4 pieces of information. Can we give a valid order in which to compute these 4 pieces of information? Well, the one observation that we can make is we can think of it, well, let's do a matrix. Just like we did for question number 2, let's do a matrix for question number 4. Matrices are often a really, really good way to look at these problems. Let's say that this axis up here, I, well, this is going to be an n by n matrix. Let's say this is I, and this is j. This matrix is n by n. And we'll say that the ijth entry of this matrix is just equal to s sub ij. The first thing that we observe is that we only care about entries a sub ij such that I is greater than or equal to j, because otherwise it's meaningless, right? There's no real interpretation for I5, 1. There are no values that are greater than or equal to 5 but less than or equal to 1. So in other words, this is going to be an upper triangular matrix. Everything below the diagonal is just going to be all zeros. What about the diagonal values themselves? Well, they were actually the first thing we looked at. They're what we called these simple cases right here. S sub 5, 5, S sub 1, 1. We can immediately fill in the diagonals of this matrix with just the values that are shown to us on the cards. A1, A2, A3, all the way right here through AN minus 1, AN minus 2, AN minus 3, right? And we can see that our goal, our target value, which is just going to be S sub 1n, the best score when we're looking at all the cards, 1 through n, is the top right entry of this matrix, right here. So, does our recurrence relation give us a valid way to get from the diagonal to this entry right here? And also, this is not a 0 there. I'll put a box there instead. This is our desired value. These are the trivial values we start with. Does our recurrence relation give us a way to get from the trivial values, the base cases, to the target? The answer is yes. And we can do that by looking at diagonals of this matrix once again. Namely, S sub ij, let's say it lies along this diagonal right here, right? This is ij. What do we need in order to compute it? And let's also draw 2 diagonals to the left of it. This diagonal and this diagonal. Well, in order to compute it, we need I minus 2j, all right, that's going to be right here. We need I minus 1j minus 1, all right, that's going to be right here. And we need ij minus 2. That's going to be right here. So we can see that to compute the values on the nth diagonal, all we need are all the values on the n minus 1st diagonal and the n minus 2nd diagonal. So to compute diagonals going all the way from the main diagonal of the matrix to our target, we can simply go in order, traversing all along this diagonal, all along the next diagonal, all along the next diagonal, until we get to our target. This gives us very similar runtime and space as the algorithm for number 2. Namely, we'll have n squared subproblems to compute. We can verify that each one is constant time, which they often but not always are in DP. The constant time is just going to come from this comparison right here. That's one comparison. This is a second comparison. We have 2 additions to perform, and then we have 1 more comparison. That's 5 operations total. 5 is a constant. So we have O of n squared times O of 1 for our runtime. Just like before, the naive solution storing this entire matrix in memory would also be O of n squared space. But we only need to remember 2 previous diagonals at a time, so really we can narrow this down to O of n space. And that is going to be our polynomial time linear space algorithm for coming up with the optimal strategy to this card game. You've now seen how to formulate DP solutions to 3 relatively canonical problems. Each of these problems is of roughly the same difficulty that you could see on a midterm or an exam. So if you feel confident with the process by which we came up for the solutions for these, you should feel confident that you stand a good shot at approaching a similar problem on a midterm or a final. We're also now going to look at question number 3, which is a much more challenging variant of dynamic programming and is included here more for your own intellectual exercise. Complementary connected components. I'll first discuss a bit of notation which you may or may not have seen before, which is this O tilde. O tilde is a variant of O in which we ignore logarithmic factors. For example, an algorithm that's O of m plus, an algorithm that's O of m plus n times log to the 10th m log to the 5th n is still going to be O tilde of m plus n. As we know, linear factors dominate logarithmic factors, so O tilde is just giving us a way of focusing on the linear behavior while ignoring the logarithmic behavior. And that's what we're looking for in this problem. So let's discuss how we could come up with a DP solution to this. What is an idea for a subproblem? Well, since this is defined as looking at a vertex set 1 through n, an obvious idea for the subproblem is just a smaller vertex set. Let's say 1 through k. So we're just going to generalize a little bit and say, how can we answer this problem for vertices 1 through k? Before we proceed, it's worth discussing a little bit more what this problem is asking for, because it's not entirely obvious. We know how to find connected components in just a graph, right? Let's say these are our vertices. We have 2 connected components here. This guy and this guy, right? What we haven't seen yet is how to count connected components in the complement of a graph. So if this is our graph, right? Maybe what I want to look at instead is the complement, meaning all of the edges that aren't originally in this graph. So we're going to look at all of these edges, and I'm going to miss a couple because there are a bunch of vertices in here, but we can basically see it'll be something like this red graph. This red graph is going to be G prime, and here we have only a single connected component in G prime, even though we had 2 connected components in G. So as you can see, the problems at first may seem to have very little to do with each other, except for the fact that they're sort of roughly inversely proportional. And this is a very, very rough, intuitive outline of the problem. If we have a lot of connected components in G, we're probably going to have very few in G prime, and the other way around. If G basically consists of 1 big connected component, it's likely that G prime will consist of many sparse disconnected components. But how can we actually go about computing the number of connected components in the complement? It's worth stating ahead of time that just taking the complement. So I'm wondering briefly why we can't just take the complement of the graph and then run the connected components algorithm on that. And it's possible that we can. There might be a sort of hiccup in there that I'm not thinking of right now. But either way, there's a really nice DP algorithm to solve this problem that we're going to go over. So let's look at these subproblems. Let's assume, so we're going to try and compute a slightly larger subproblem in terms of a slightly smaller subproblem. So we can assume that we already know the connected components in the complement of G, considering only the first k vertices. And now we're going to try and figure out the number of connected components in the complement of G, considering the first k plus 1 vertices. So let's say that we've run our 1 through k algorithm. We have that these are the connected components of G prime. Note that this is going to be a partition of 1 through k. Let's even say it's a partition such that we have 5 vertices in the first component, 3 here, 2 here, 2 here, and then maybe only 1 in this last connected component. So here, by addition, k is 13. Now we're going to add the 14th vertex. Let's call it v. What we want to figure out is what the addition of v to the graph does to these connected components. We can basically see that we can sort of start to think about what the cases are, right? It could be the case that the addition of v just leads to v becoming a whole new connected component all by itself. That's one option. It could also be that v just merges into one of the existing connected components, right? And this just becomes a 6. That's another option. There's a slight elaboration of this case where v belongs to multiple connected components in G prime. Let's say it belongs to both of these. Then these two will get merged with each other and have v added to them to form a new connected component of size 5. These are actually all the cases. Basically, we can have v forms its own component, v joins exactly one existing component, or v joins multiple existing components and merges them. In terms of the effect on the number of connected components that we're going to have, we can see that this adds 1, this adds nothing, and this is actually going to subtract a certain number from the number of connected components. So these are all 3 cases. The structure of these cases may remind you of a data structure that we've already gone over in this class. The disjoint sets union implemented with the tree union data structure that we have already seen in lecture. So we're actually going to use one of those to keep track of these connected components. As we go through, we're only going to use a single one too, but we're going to use 2 different heaps to store the connected components in 1 through k and 1 through k plus 1. We're going to start off with all of these connected components in the first heap, right? So we're going to have our 5 guy, we're going to have our 3, our 2, our 2, and we're going to have our 1. Then we're going to take a look at v, and we're going to take a look at all of the edges from v, which in this case v is the 14th vertex, all of the edges from v to its neighbors in G. Right? So in this case, U is going to have 13 neighbors. We'll call them U1, U2, all the way through U13. And note that all of these are edges from G. Now, our goal is to figure out how to determine which of these cases we're in based on the edges from V to U1 through U13. Well, what happens if every single one of these and so here's also a key point. I put U13 here, but it's possible that these edges don't exist for all of these U's. Like it could be that there is an edge from V to U1, but there is no edge from V to U2. this is actually in the random graph most likely what's going to occur. We're going to have edges from V to some of the U, but not to others. Well, if we have edges from V to every single one of the U, U1 through U13, then that means that in the complement of G, there is no edge from V to any connected component. Because if there were an edge in the complement of G from V to, let's say, this top connected component, then that would mean that in G itself, and we'll even say that the vertex in here that's connected to is, let's say, U7, that would mean if the edge V U7 is in G prime, that V U7 is not in G. But if we figure out that all 13 of these edges are present, then that means that this cannot be the case. So V must be in its own component. And that's this first case. This also leads to an interesting method of analysis for how we could possibly go about discerning between the rest of these cases, which is we'll iterate through these edges, and as we iterate, we'll keep a count of the number of edges in G from V to each connected component. So let's do this. Let's look at each of these edges one by one by one by one by one. And as we do it, we'll start counting. So let's say the first edge that we look at from V to U1 is from here to this guy down here. We're going to say, okay, let's put a 1 right here. The next edge is from V to this guy. Let's count that too. Next edge is from V to this guy. Let's count here. Next edge is from V to this guy. We'll go up to 2. And let's say we run through this whole thing and we get 5 edges here. We get 2 edges here, 2 edges here, 1 here, and 1 here. Well, specifically, we can see that we discovered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges. So that meant that 2 of these edges were not present in G, right? So maybe we'll say that the 2 that were not present were from V to U3 and V to U4. V to U3 and V to U4 were not present in G. What does that mean? It means V to U3 and V to U4 are present in G prime. Well, so now we know that whichever connected component U3 lies in is connected to V in G prime. Whatever connected component U4 lies in is connected to G, is connected to V in G prime. How do we figure out which connected components U3 and U4 lie in? Well, we look at these counts. Namely, we look at each of the connected components where the number of edges from V to that connected component is different from the number of vertices. Here, this first connecting component, we have 5 vertices and we have 5 edges from V to that connected component. So that means this guy is not connected to V in G prime. But here, we have 3 vertices, but only 2 edges from V to that connected component, right? There's no third edge right here. That means that in G prime, there is an edge from V to this guy. And that means that in G prime, they are connected to each other. So that means we merge V with this second connected component right here. Similarly, this second to last connected component is also missing an edge, which means that there is an edge in G prime between this connected component and V, which tells us that we lie in this case. V merges these 2 connected components. This is actually all the logic we need in order to compute the merge step. Now, how do we implement this step? Simple. We iterate through the vertices, computing these counts. All of the connected components start off in our left heap, and as soon as the edge count is equal to the vertex count for a connected component, let's say this guy, we move it to the right-hand side heap. And what it means to move a connected component from the left-hand side heap to the right-hand side heap is that it's disconnected from V in G prime. We keep on going. In this case, we saw that eventually 5 edge count equals vertex count. Here, edge count equals vertex count. So move this guy. And here, edge count equals vertex count, so we'll move this guy, that each of these three connected components remains disconnected from V and G prime. But these two, this and this, these two right here, merge with V. And that's how we perform the update step. We walk through all the edges from V to its neighbors, remembering, since we're looking at subproblems, to only look at the neighbors whose vertex value, this is just enumeration of all the vertices, is less than itself. So if we're looking at the 14th vertex, we only look at its first 13 neighbors. And then, once we've run through all of them, all of the connected components that have the same number of edges to V as vertices in the set, we leave for the next step as their own connected components, and all of the ones that have a smaller edge count than vertex count, we merge with V to form their own connected component. So, this heap right here, we're going to take V, we're going to throw it into this connected component to get one of size 6, and then we're going to throw this whole thing into our heap. And this right here is the set of connected components in G prime for vertices 1 through k plus 1. Once we've computed this, we can just do another step. We can take a look at I15 right here. I equals 15. We'll get a new V, V15. We'll look at all of V15's neighbors, U1 through U14, remembering that all of these might not exist, and merge with the exact same process with another heap down here, and then we'll get the connected components in I1 through 16, and 17, and 18, and so on, until we get the connected components in G prime, considering all n vertices. Now, I ran through this argument kind of fast, and it is a difficult argument to make, so I suggest the possibility of rewatching it. I suggest the possibility of taking this only as a hint and trying to work through all the details yourself. Overall, if you do this, you'll get a sense for the power of DP algorithms, because remember, we only have to remember 2 of these heaps at a time, just like how in the other matrix-based DP, we only had to remember 2 previous diagonals at a time. So really all we need is 2 heaps and a linear time merge step to give us an O of n squared algorithm for this relatively complex problem using space O of n, because each of these heaps can have at most n vertices in it. This is a difficult problem, and it's okay if you found this a little bit confusing. In general, you'll see a lot more DP problems in homework over the next couple weeks, and I suggest you approach them all kind of similar to the way we approach them today. You try and look at subproblems. You try and break those subproblems down into a recurrence relation that allows you to compute one in terms of the previous one. And then you make sure that those recurrence relations actually give you a valid order for resolving and computing them that'll lead you from trivial cases, like our cases on the diagonal here, to target cases, which are really complex and difficult to otherwise compute. Thanks for watching this. I hope this helped, and I'll see you all next week.